When you think about a large language model, it seems pretty simple, right? It reads text, it writes text. But that's just the surface. Behind the scenes, it's actually living two totally different lives, one called training and the other inference. And let me tell you, from an engineering and a business point of view, these two are like night and day. They've got different rules, different goals, and, you guessed it, wildly different price tags.
All right, to really get a handle on this, let's use a little metaphor. Picture training as the model's growth phase. This is its childhood and college years all rolled into one. It's hitting the books, building its brain, just soaking up all the knowledge it can. Then you have inference. This is the model's social phase. It's graduated, it's out in the real world, using everything it learned to actually hold a conversation and get things done.
Okay, so here's what we're going to cover. First, we'll break down the big difference between growth and performance. Then we'll look at what they actually have in common. After that, we'll get into the nitty-gritty of writing versus reading knowledge, the whole compute versus memory battle, what this all really costs, and finally, what it means for strategy.
All right, let's jump right in. Growth versus performance. This is really the core of it, whether the model is in the middle of learning or just doing. So here's the absolute key difference, the thing you have to remember. Training is a write operation. It's dynamic. The model is literally rewriting its own brain, constantly updating its parameters. It's like a student just cramming for an exam, writing notes, crossing things out, making corrections. But inference, that's a read operation. It's totally stable. The knowledge is locked in, frozen. The model is just executing. It's like a grad who's already passed the exam and is now just using what they know.
Okay, we've talked a lot about the differences. But before we go any further down that road, we need to talk about what they have in common, because there's one core engine that they both share. This is where it all begins.
So whether it's training or inference, everything, and I mean everything, is built on this one process called the forward pass. Honestly, you can just think of it as the model's basic thought process. It's like a little assembly line inside its head that takes our words, turns them into math, and figures out, okay, what's the most likely word to say next? And this assembly line has four main stations. First up is tokenization, which is just a fancy way of saying it chops up our text into little pieces and gives each one a number. Then comes embedding, which takes those numbers and plots them on a huge complex map of meaning. Next, the transformer blocks. This is the real brain power. They look at where all those points are on the map to figure out the context. And finally, you get logic generation. This is the model calculating the odds, the raw probability, for every single word in its vocabulary that could come next. So that's the shared engine. Now let's see how that same engine is used to power two totally different loops of operation. This is really where training and inference go their separate ways. Okay, so training. It's this intense, grinding loop. First, it does that forward pass we just talked about to make a guess. Then, it immediately checks its work and calculates something called loss, which is just a score for how wrong it was. Here's the magic part. It then uses that error to do a backward pass, or backpropagation, to figure out exactly which of its billions of little knobs, its weights, it needs to tweak. The optimizer makes the change, and then it does it all over again, and again, trillions of times. Now compare that to inference. It's so much simpler. It's just a clean generation loop. It does the forward pass, picks a word, adds it to the sentence, and loops back to do it again for the next word. That's it. No checking for errors, no backward pass, no rewriting its brain. The real clever part here is the KV cache. Think of it like the model's scratchpad. It jots down what it's already calculated so it doesn't have to start from scratch and reread the whole conversation every time it wants to add a single new word. Super efficient.
All right, so these two totally different loops, they basically declare war on the hardware. The things that slow down training are the exact opposite of what slows down inference. So as an engineer, you're forced to pick a side. Are you building a system for raw, brute force calculation, or are you building it for speed of late data delivery?
And this image just nails the problem. Training is compute-bound. It's all about raw mathematical muscle. Its speed is limited by how many calculations the GPU can crank out per second. We call that flops. But inference, it's memory-bound. It's not about how fast the calculator is. It's about how fast you can feed it numbers. The bottleneck is the pipe, the memory bandwidth, not the processor. So why this massive traffic jam during inference? Well, think about this. For every single token the model generates, its entire library of knowledge, we're talking hundreds of gigabytes of weights, has to be moved from the memory chips over to the processor. It's insane. You've got this supercomputer-level calculator that's just sitting there, twiddling its thumbs, waiting for the data to show up. It's a huge waste. Okay, so this technical fight between being compute-bound and memory-bound, it doesn't just stay in the data center. It has massive, and I mean massive, economic consequences. If you're in a business that uses AI, you absolutely have to understand this. And the best way to think about the money is with the classic iceberg analogy. The training cost, that's the part you see above the water. It's a huge one-time bill, a capital expense or CapEx. But the real danger, the part that sinks ships, is what's hidden underneath. That's inference. It's the day-to-day, month-to-month operational cost, the OpEx. And get this, it can make up 80 to 90% of the entire cost of running an AI over its lifetime. And don't get me wrong, that tip of the iceberg is not small. Let's put some real numbers on it. If you want to train a big 70 billion parameter model today, you're looking at firing up over 1,000 H100 GPUs and letting them run 24/7 for a month. The price tag for just the compute, somewhere around $3 million. And that's just the start, before you pay for your data, your engineers, everything else. So this huge cost difference forces a really important strategic question on every company. When does it actually make financial sense to bite the bullet, pay that massive upfront cost, and run your own model, versus just paying a company like OpenAI or Google every time you use their API? Well, the math is pretty clear. There's a magic number, a break-even point, and that number is about 330 million tokens. If you think your app is going to process more than that over its lifetime, then believe it or not, it's actually cheaper to build it yourself, even with that scary multi-million-dollar price tag for training. So where does all this leave us? What does it mean for strategy? It means the game is changing. For a long time, it was all about building the biggest, most powerful model. But now, the focus is shifting. It's about building the most efficient one.
Think of it this way. Training is like building a monster engine. It's all about raw, brute force horsepower. But inference, that's about building the Formula One car around that engine. It's about aerodynamics, fuel efficiency, precision, all the things you need to actually win the race. And today, if you want to win in AI, you can't just have a powerful engine. You need the whole efficient package.
So this changes the questions you need to be asking. It becomes a checklist. First, are you going to blow past that 330 million token mark? If yes, you should think about self-hosting. Second, is speed, is low latency a make-or-break feature for your product? If so, you need to invest in your own infrastructure. And third, and this is a big one, does your team actually have the chops to optimize for inference? Can they do things like quantization and manage that KV cache to squeeze out every drop of performance?
Which brings us to a final thought to leave you with. For so long, the story of AI has been about bigger, stronger, more powerful. It's been a story of raw scale. But as we're starting to see, the really hard, really expensive problem isn't building the intelligence, it's running it efficiently. So maybe, just maybe, the next true genius of AI won't be the person who builds the most powerful model, but the person who figures out how to run it with the most radical, elegant efficiency.